Today we'll discuss the binomial distribution. The binomial distribution is all about probabilities revolving around two events. The bi suggesting the number 2, such as bilingual, 2 languages, or bicycle, 2 wheels, or bilateral, 2 sides. For the binomial distribution, we're talking about probabilities around two events that can be thought of as a 0 or a 1, pass or fail, success or failure, etc., where there are always only two possible outcomes per event. Now let's examine a simple toss coin experiment as we've done before, and we'll expand on it. For a toss coin, it's either head or tail, and assuming a fair coin, the odds are always 50-50. Now what happens if we keep on repeating the experiment, tossing the coin, let's say 3 times? What is the probability of getting 1 head, of 2 heads, or 3 heads respectively? Obviously, it's not just the 50-50. For this, we need to work the binomial distribution. But before we show the formula, let's break down the intuition first that leads up to the formula. First, let's define H as head and T as tail. And we know we have to do 3 tosses. So what are all the outcomes? Well, there are 2 outcomes for each of the first, the second, and third tosses. So that's 2 to the power 3 or 8 outcomes we're expecting. Now let's list them down as follows, and here's a table. If you take a look at event 1 and event 8, it's pretty straightforward. There's only one way to get 3 heads and only one way to also get 3 tails. Now, how about getting 1 tail? Well, it can be either at the start or the middle or at the end. So there are 3 ways as listed down in the table. How about getting 2 tails? Well, it's the same as getting 1 head, either at the start or the middle or at the end. So it's also 3 as listed in the table. Now, here's a question. How can we get the numbers above without the tedious enumeration we did above? Well, it's easy. We just use the combination formula. Wait. Why combinations and not permutations? Let's talk about events 2 to 4. If we were talking about permutations, that would imply that there are 2 kinds of H's. But obviously, these are outcomes and not unique items in a set like H1 or H2, for example. The same is true for events 5 to 7. We are talking about the same T's and not 2 distinct T's, T1 and T2. Therefore, this is not about arrangements of distinct items per se, but selection. Now, consistent with mathematical literature, let's use the notation NK to mean the combination of n items taken k at a time. So, events 2 to 4 can be thought of as the actualization of 3 combination 1 of 3 events where there's only 1 tail. And here's the formula. Note that this is like having 1 placeholder, then choosing how many ways we can fill it up. And there are 3 ways. Divided by the number of ways of arranging 1 placeholder, which is just 1 factorial, a trivial exercise, like so. Now, events 5 to 7 can be thought of as the actualization of 3 combination 2 of 3 events where there will be 2 tails. And here's the formula. This is like having 2 placeholders, 3 times 2, then divide by the number of ways of arranging the 2 items, 2 factorial, and we have this formula. And we're showing a summary in the table below. Okay, so what is the probability of getting 1 head for a fair coin, given 3 tosses? Well, whatever that probability is, it will happen 3 times since there are 3 combination 1 ways of getting 1 head. But what exactly are the probabilities? So in 3 tosses, the probability of 1 head and therefore 2 tails is actually 0.5 raised to the power 1 times 0.5 raised to the power 2 using compound probabilities. But remember, this happens 3 times. So the actual probability of getting exactly 1 head in 3 tosses is as follows. 3 combination 1, 0.5 raised to the power 1 times 0.5 raised to the power 2, which is equal to 0.375. Okay, how about the probability of getting 2 heads in 3 tosses? Well, that would be 3 combination 2 times 0.5 raised to the power 2 times 0.5 raised to the power 1, which is equal to 0.375. And finally, how about the probability of getting 3 heads in 3 tosses? Well, that would be 3 combination 3 times 0.5 raised to the power 3 times 0.5 raised to the power 0, which is equal to 0.125. And here's a table that outlines all that discussion. In general, the probability of k successes in n events is n combination k times p to the power k times q to the power n minus k, where q is equal to 1 minus p. Now let's work on 10 tosses and use directly a spreadsheet solution, a copy which can be downloaded below. What is the probability of getting exactly 4 heads? Taking a look at this table, we find that the probability is 20.5078%. Now, what is the probability of getting heads between 4 and 6 times endpoints inclusive? This just means adding the probability of getting 4, 5, and 6 heads, which adds to 0.656250. Now take a look at both the distribution of the combination column and the probabilities under the product label in this table. Notice how if we put them in a chart, they look like a bell curve. Now this will lead us to our next point as to why the binomial can look like a normal distribution. If we flip a coin 100 or even more than 1,000 times, calculating every combination by hand is tedious. But here's something amazing. When n is large, the binomial distribution starts to resemble the familiar bell curve of the normal distribution. So the normal approximation uses the mean and standard deviation of the binomial, where mu is equal to n times p, and standard deviation sigma is equal to the square root of n times p times q. Then we can approximate the probability of x between a and b to be equal to this, where we have this 0.5 adjustment. It's a continuity correction since we're approximating a discrete distribution, the binomial, with a continuous one, the normal. We'll have an example later to show this. So going back to our problem with 10 tosses, what's the probability of getting between 4 and 6 heads using a normal approximation? Well, we know that n equals 10 and p is equal to 0.5. Therefore, mu is equal to 10 times 0.5, which is equal to 5. And sigma is equal to the square root of 10 times 0.5 times 0.5, which is roughly 1.58. Now, using the continuity correction, we use 3.5 to 6.5 instead of 4 and 6. That's because anything above 3.5 to almost 4 gets rounded up to 4, while numbers above 6 and below 6.5 gets rounded down to 6. We now convert these to z-scores, and we have negative z is equal to negative 0.94868, and positive z is equal to 0.94868. Then we check the standard normal table for z, or we'll just use Excel. We'll find the probability using NORMSDIST in Excel. Remember that in Excel, NORMSDIST gives a one-tail probability to the left of z. So kindly check our statistics crash course where we discuss all about this. Anyway, so we do the following. We get the area to the left of z equals 0.94868 and subtract by the area to the left of negative z, negative 0.94868. And we find that we get the probabilities 0.828609 minus 0.171391, which is roughly 0.6572. Notice how close this is to the actual binomial distribution solution of 0.65625. So we can say there's about a 65.72 chance using the normal approximation versus the 65.63 using the binomial distribution of getting between 4 and 6 heads. Now imagine how simple this is if we're working on hundreds or even thousands of toss coin experiments. To sum up, the binomial distribution counts successes in n independent trials. Combinations, meaning n combination k, tell us the number of ways to get exactly k successes. For large n's, the binomial can be approximated by a normal distribution using the mean and standard deviation. Alright, if you enjoyed this video, hit like and subscribe or just write a comment below to help support the channel. See you next time!